Let's talk some more about polygons. We've already considered triangles and quadrilaterals, so we'll continue on with polygons that have more than 4 sides in this video. We can classify a polygon as either regular or irregular. Regular polygons have all sides the same length and all interior angles have the same measure. Let's look at some regular and irregular polygons. Here we have a regular triangle, otherwise known as an equilateral triangle, equal angles or congruent angles, and congruent sides. A regular quadrilateral is a square, 4 congruent sides, 4 congruent angles. If I move one of these vertices, it becomes an irregular quadrilateral, where the angles don't all match and the sides have different lengths. We can have a regular polygon or an irregular polygon, and so on and so forth. When all of the sides are congruent and when all of the angles are congruent, it would be a regular polygon. In addition to sides and angles, we can consider diagonals. So let's draw a pentagon. And if I were to connect non-adjacent vertices, then I would have a diagonal. So non-adjacent, here's an example, that's a diagonal. We don't connect adjacent vertices because that's just the edge. It wouldn't be considered a diagonal. We'd have to do a non-adjacent vertex. So let's look at some interactive polygons. First, we'll go with quadrilaterals. Some of the diagonals of quadrilaterals have some pretty interesting properties. If we look at a square, you can see that the diagonals bisect each other, they cut each other in half, and they form a right angle where they intersect. But if I switch to a rectangle that's not a square, so if I make the sides not congruent, then you can see that the diagonals still bisect each other, still cut each other in half, but they aren't anymore at a right angle. If I go with something like a trapezoid, then the diagonals don't necessarily bisect each other, they don't cut each other in half, and they don't necessarily meet at right angles. So notice that triangles don't have diagonals. And if we start to go to the polygons with more sides, then the diagonals form some fun patterns here. With our regular pentagon, or any pentagon, we can see that each vertex has 2 possible diagonals. With the regular hexagon, each vertex has 3 possible diagonals, and so on. We can also classify polygons as either convex or concave. On the left, we have a convex polygon, and on the right, we have a concave polygon. The concave polygon looks like it's caving in, but we can get more technical than that on our understanding of convex versus concave. First, we'll look at angles. The interior angles on a convex polygon are all less than 180 degrees. Recall that a 180-degree angle is a straight angle. It's a straight line right there. So all of these angles are less than 180 degrees. On a concave polygon, you can see that here the interior angle is more than 180 degrees. When we consider diagonals, all of the diagonals on a convex polygon fall on the interior of the polygon. On a concave polygon, we can have a diagonal that's on the exterior. Let's talk a little bit more about those interior angles. Interior angles are the angles inside a polygon that are formed by 2 sides. So if we have a vertex and the 2 sides, that would be an interior angle. As we just saw, the interior angle can be more than 180 degrees on a concave polygon. It turns out that it can be pretty useful to know something about the sum of the interior angles of a triangle, our simplest polygon. It turns out that the sum of the interior angles of a triangle is always 180 degrees. It can be helpful to convince yourself of this fact. We're not going to do a formal proof, but we are going to do an elementary appropriate understanding of the sum of the interior angles of a triangle. So I have three triangles here. I have a right triangle, I have an acute triangle, and I have an obtuse triangle. And what I'm going to do is I'm going to take each interior angle and I am going to rip it off, and then I'm going to line them up and see that they form a straight angle. So they form 180 degrees. So in other words, the interior angles add up to 180 degrees. Here's my right triangle, and we put the three interior angles together, 180 degrees. Doesn't matter what kind of triangle I do. There's my acute triangle. The three angles together, I get 180 degrees. If I take my obtuse triangle, guess what happens? I put the three angles together and I end up with 180 degrees. So if I add the measure of the angles for the triangle, it'll always be 180 degrees. Here we are at our good old interactive triangle, and we could build any triangle that we want to, and when we add those angles up, it'll always be 180 degrees. If we switch over to the quadrilateral and start with a square, we can see four right angles, four 90-degree angles add up to 360 degrees. If I change to a different quadrilateral, let's go with a parallelogram here. 103 plus 77 is 180. 180 plus 180 is 360. With any quadrilateral, if I add up the angles, it'll add up to 360. Let's look at this more deeply. So let's draw a quadrilateral, a convex quadrilateral, and let's draw a diagonal to break it into two separate triangles. And I can notice with the triangle on the left, I know that the three angles will add up to 180 degrees. And with the triangle on the right, I know that the three interior angles will add up to 180 degrees. So together, that makes 360 degrees. That worked because the interior angles of the triangle combined form the interior angles of the quadrilateral. It doesn't matter if I have a concave quadrilateral. I can still break it into two triangles and still look at the interior angles of both triangles and see that combined, the interior angles of both triangles make up the interior angles of the quadrilateral. So since it was two triangles, I end up with 360 degrees. We could go a little crazy with this. So if I do another quadrilateral here, pretend I have straight sides, and what if I did two diagonals? You might think that this doesn't work. Well, it still works, we just have to go a little bit harder. So I have four triangles, so this is 180 degrees, four triangles, 720 degrees, which is definitely not 360. But what you have to notice is that for any given triangle here, one of the angles did not contribute to the interior angles of the quadrilateral. So what we'd have to do is notice that these omitted angles together form 360 degrees. So I can take my 720 from all of the triangles, subtract away the angles in the middle that didn't contribute to the quadrilateral's interior angles, and I'd be left with 360 degrees. We can extend this strategy to any polygon. Let's do a pentagon next. So pretend that these are straight sides here. And I can break it into, this time, three triangles. So I like to do the strategy where I don't have to subtract off extra angles. I can see that the interior angles of my pentagon come from the three triangles. Each triangle contributes 180 degrees. I have three triangles. So the sum of the interior angles of a pentagon is 540 degrees.